You ever wonder how your email inbox just knows what spam is? Or how a website can recommend a movie you'll actually love? Well, it often starts with a really powerful idea, learning from examples that already have the answers. And that's exactly what we're going to dive into.
Welcome! Today we're going to break down one of the most fundamental concepts in all of machine learning, supervised learning. We're going to see how we go from drawing simple lines all the way to building models that can make some pretty smart decisions.
So, how does this all work? Well, the core idea is surprisingly intuitive. It all comes down to one thing: labels. Supervised learning is, pretty much exactly what it sounds like. We act as the supervisor or the teacher. Just imagine you're teaching a computer with a huge stack of digital flashcards. On one side of the card, you have an input, like a picture of a cat. And on the other side, you have the correct output, the label, which is just the word cat. The model's job is to study thousands or even millions of these labeled examples until it finally learns the patterns.
The whole process really breaks down into 3 simple steps. First, we feed the model tons and tons of that labeled data. Second, the model churns through it, adjusting itself over and over until it gets really good at matching the inputs to the correct outputs. And finally, once it's trained, you can show it something brand new, something it's never seen before, and it can make a confident prediction.
All right, so let's start with this super common problem. How do you predict a specific number? How do we build a model for that? For that, we use an algorithm called linear regression. It's one of the most famous tools in the machine learning toolbox, and its whole goal is to find a clear, straight-line relationship between different variables.
The core idea here is really visual. Imagine you plot a bunch of data points on a graph, like, say, years of experience versus salary. Linear regression just works by drawing a single straight line through all that data. The goal is to find the one line that best fits all the points by getting as close to them as possible. It's kind of like the ultimate trend line.
So, at the end of the day, you use linear regression whenever you're asking how much or how many. For example, based on a person's height, what's their predicted weight? Or based on a house's size, what's its likely price?
Okay, so that works great for numbers. But what happens when the answer isn't a number at all? Yeah, a straight line is perfect for predicting a value on a spectrum, but it can't really help us predict a simple yes or no. This is a totally different kind of challenge called a classification problem, and for that, we're going to need a different tool.
And that brings us to logistic regression. So while linear regression predicts a continuous number, like a house price, logistic regression is built for a different job, predicting a category. The classic example is this email spam or not spam?
See, instead of spitting out a number, it gives you a probability, a score that's always between 0 and 1. So it might tell you, hey, I'm 95% sure this email is spam, or I'm only 10% sure this credit card transaction is fraudulent.
So then that probability gets turned into a final decision. It's actually super simple. By default, if the score is over 0.5 or 50%, the model predicts yes. If it's below that line, it predicts no. It's just a simple threshold that turns that probability into a clear, actionable choice.
All right, so we can predict numbers and we can predict simple choices. But what about more complex decisions that have a bunch of different factors? Well, for that, we can think kind of like a flowchart.
And this brings us to the decision tree. This is one of the most intuitive models out there because it works just like we do. It makes a decision by asking a series of simple, cascading questions to get to the final answer. And because you can literally see the logic, it's known as a white box model. It's super easy for us humans to understand what it's doing. The structure is pretty straightforward. You start at the very top with all your data. That's called the root node. Then, the tree asks a question that splits that data into smaller groups, creating what we call internal nodes. This just keeps happening, splitting and splitting until you finally reach a final answer at the bottom, which is a leaf node.
But here's the magic part, right? How does the algorithm figure out the best questions to ask and in what order to get to the right answer? Well, it uses a clever metric called Giannini impurity. Now that sounds complicated, but it's really just a score that measures how mixed up a group of data is. So imagine a basket of fruit with only apples. That's a pure group, and its Gini score is 0. But a basket with half apples and half oranges is impure. The algorithm's goal is always to ask questions that create the purest possible groups.
So what the tree does is it tests out every single possible question it can ask about the data. It might check, is the person's age over 40? Or, is their income above $50,000? And then it picks the one question that causes the biggest drop in that impurity score, the one question that does the absolute best job of sorting the data into these pure little subgroups. So we've looked at 3 really different models, and each one has its own unique way of learning from data. So what's the big picture here? What's the takeaway?
This summary table really lays it all out. If you're predicting a number, like a price, you're probably going to reach for linear regression to find that best fit line. For a simple yes or no choice, like spam detection, logistic regression is your go-to for getting a probability. And for more complex decisions that involve a lot of factors, a decision tree is fantastic because it asks a series of sorting questions. And here's the most important takeaway of all: there's no single best algorithm. There's no magic bullet. Success in machine learning is often less about knowing complex math and more about understanding your problem really, really well, and then choosing the right tool from the toolbox for that specific job.
And that leads to a final and really critical thought. These models are powerful because they learn patterns from the data we give them. They learn from the past. But what happens if that past data contains hidden biases? Well, the model will learn those biases too, and that is one of the biggest challenges in AI today. Figuring out how these powerful tools might also learn our own hidden prejudices.
Welcome back to the deep dive. Today we're really focusing on what you could call the engine room of predictive analytics, supervised learning. This isn't just about, crunching numbers. It's about taking labeled data inputs that are explicitly paired with the correct outputs and teaching a machine the logic.
Yeah, the mapping.
Exactly, the mapping, so it can predict the unknown.
It really is the core definition of predictive modeling. I mean, the sources are pretty clear.
Yeah.
The mission is to build that relationship between X, your features, your input,
Okay.
and Y, the outcome, that's solid enough, robust enough to give you accurate predictions when you show it completely new data it's never seen before.
So our mission today is to explore, let's say, 4 critical tools in that toolkit. We'll see how these models go from simple straight line assumptions to things like geometry, optimizing purity, and even maximizing these really complex boundaries.
Sounds good.
Let's start with the classic. Quantitative prediction. Linear regression.
Linear regression, I mean, it's the anchor algorithm, isn't it? It's fundamental in statistics, in machine learning, and it works off a pretty simple idea about the world.
It really does. It assumes linearity. That's the core. Linear regression, or LR, it's built on the idea that there's basically a straight line relationship between your input factors and your single numerical output.
Yeah.
Think of it like this. If you increase the input by 1 unit, the output changes by a fixed predictable amount. It's, linear.
And the model's whole job is just defining that line. So if you're trying to predict, say, income based on years of experience,
Yep.
the algorithm figures out the best intercept and slope, those coefficients that define the relationship. And if you only use one input, that's simple linear regression.
Right.
If you use more experience, education, location, whatever, then it's multiple linear regression.
Exactly. And the key focus here is minimizing the error. How do we train it? We use a technique called ordinary least squares OLS.
OLS, right. Conceptually, what OLS does is find the best fit line. It draws a line through all the data points, measures the vertical distance from each point to the line,
Okay.
squares those little distances, those errors, and then finds the one line that makes the total sum of those squared errors as small as absolutely possible.
It's a really neat geometric solution when you think about it. But okay, once you have that line, how do you tell someone, like a stakeholder, how good the model actually is? You can't just give them the raw error sum.
No, exactly. And that's where the coefficient of determination, the R-squared value, becomes probably the most strategic metric. Forget the complex algebra for a second.
Yeah.
What R-squared tells you is the fraction of the variability in your outcome variable, the Y, that your model actually managed to explain. So an R-squared of 0.8 means your model captured like 80% of the movement in the data.
But I think the real insight there is focusing on the other bit, the 20% your model didn't capture.
That's crucial.
Because that 20% tells you where to look next.
Right.
It highlights what variation is still out there, unexplained. It makes you think, okay, do I need more features? Or maybe this linear thing just isn't the right approach here.
Precisely. It guides your next steps.
Okay, so that handles continuous numerical predictions, things like weight, salary, temperature. But what happens if the outcome is categorical? If we're classifying emails as spam or not spam, or figuring out if a customer will buy or not buy, linear regression just breaks down.
Oh, completely. It fails because linear regression can output, well, any number.
Yeah.
It could predict -10 or +500.
Right.
But if you're trying to predict the probability of something happening, that number absolutely has to fall between 0 and 1. It's logical. You can't have a 150% chance of spam or, a negative probability.
Yeah.
It just doesn't make sense.
Which means we have to switch gears. We need logistic regression, log-R. Log-R is built specifically for these dichotomous outcomes. Yes, no, true, false kinds of situations. The underlying calculation is still, well, linear, but it's the transformation that's the magic trick.
Exactly right. Log-R uses the sigmoid function. It mathematically squeezes that linear output, whatever it might be, into the required 0 to 1 range.
Like squashing it down.
Yeah, imagine taking an infinitely long straight line and just bending it carefully into an S-curve shape. Any point on that S-curve now represents a valid probability between 0 and 1. And this forces a really fundamental shift in how we actually train the model. Remember, for linear regression, we used ordinary least squares to minimize the error.
Yep. Minimize the squared distances.
Well, for logistic regression, we can't do that. We have to use maximum likelihood estimation, or MLE. The whole strategy changes. Instead of minimizing distance, we're now trying to maximize probability.
Maximize probability.
Yeah, MLE finds the set of parameters, the coefficients that make the observed data, all those actual yes and no outcomes you have in your training set, the most probable, the most likely outcome given the model. It's a much more complex, iterative, statistical fitting process.
Okay, that distinction, minimizing error versus maximizing the likelihood of what you actually saw, that feels like the key strategic nugget there.
It really is.
So, once the probability, P, is calculated using this MLE approach, the final classification is straightforward.
Pretty much. You apply cutoff. Usually it's 0.5 by default.
Yeah.
If the model spits out P equals 0.70, the prediction is yes. If P is 0.20, the prediction is no. Simple as that.
Simple thresholding.
Right. And while 0.5 is common, the sources point out, you have the strategic power to change that cutoff.
Ah, okay.
You're predicting something serious, like a high-risk medical condition. Maybe you'd set the cutoff lower, say 0.3. You'd rather catch more potential cases early.
Even if it means more false alarms.
Exactly. Even if it results in more false positives. It's a strategic trade-off you can make based on the context.
Right, right. Okay, so now let's step away from algorithms that are sort of tied to that strict linear equation idea. Let's look at approaches based more on geometry and purity, starting with k-nearest neighbors, or KNN. This one feels more intuitive, almost like peer pressure within your data's neighborhood.
It's entirely based on distance geometry, you're right. We typically use Euclidean distance.
Just the straight line distance?
Yeah, just the straight line distance between any two data points. What's really powerful about it, though, is that this simple idea extends easily into many, many dimensions. If you have 50 features,
Okay.
you're calculating that straight line distance
Yeah.
in a 50-dimensional space. It scales up.
Okay, so let's walk through how it actually makes a prediction. Say we have a new observation, a new dot, and we want to predict its class or its value. What happens? Step 1. The model calculates the Euclidean distance between that new point and, well, every single existing training point.
Every single one. It's computationally intensive. That's a key point.
Right. Step 2. We choose a value for k. Let's say we pick k5. The model then just selects the 5 closest neighbors, the 5 points with the smallest distances to our new point.
The k-nearest neighbors.
And then the final prediction.
Well, it depends on what you're trying to do. For regression, if you're predicting a continuous value like, say, weighter, the prediction for the new point is just the average weight of those 5 closest neighbors.
Makes sense.
But for classification, it becomes a majority vote. The new point gets assigned the category that's most common among those 5 neighbors. So if 3 are class A and 2 are class B...
The prediction is class A.
Exactly. Simple majority rules.
Okay, from geometry and averaging, let's pivot to decision trees, often called classification and regression trees, or CART. Now, I think this one is great because it's so explainable.
Oh, definitely.
It gives you explicit rules, like a flow chart, and it's also the foundation for really powerful algorithms like random forest.
Absolutely. Its structure is what makes it so interpretable. A decision tree gets built through this process called recursive partitioning.
Recursive partitioning?
Yeah, it's essentially creating that flowchart you mentioned,
Yeah.
a series of if-then rules based on your data features. You start with the root node, that's your whole training set.
Okay.
Then you have internal nodes, which are the split points, the questions being asked. And finally, leaf nodes, which give you the final classification or prediction. So the really strategic question becomes, how does the machine choose the best feature to split on at each of those internal nodes?
Right. How does it pick the question?
It's all about optimizing for purity. The goal is to make the resulting subgroups after the split as homogeneous, as pure as possible. You want them to be as monochromatic, class-wise as they can be.
And how do we measure that purity?
A common way, especially for the CART algorithm, is using the Gini index, or Gini impurity.
Gini mode.
Gini ranges from 0, which means perfectly pure, like all samples in that node belong to the same class, up to, well, usually 0.5 for a 2-class problem, or 1 in some definitions, meaning maximally impure, a perfect 50-50 mix or worse. And you always want the split that leads to the lowest average Gini impurity in the resulting nodes.
Lower Gini is better.
Exactly.
Yeah.
And our source material had a fantastic example for this, predicting buys insurance.
Yes.
Features like income or gender, maybe they reduce the impurity a bit, but they still have to mix, resulting in Gini values above 0. But the feature credit score, when they split on that, it achieved a Gini impurity of exactly 0.
0. So perfectly pure groups resulted from that one split.
Instantly. That tells you right there that credit score is the single most powerful, most defining feature in that particular data set for predicting who buys insurance. Its feature importance just handed to you by the tree structure.
That's incredibly clear. Okay, that brings us to our final powerhouse algorithm for today, support vector machines, or SVM. Now, while decision trees look for the purest split, SVM is looking for the optimal separating boundary.
That's a great way to put it.
Let's use that analogy again. You've got 2 groups of dots, maybe red and blue, scattered on a plot. SVM tries to find the widest possible street that can separate the red dots from the blue dots completely.
Yes, that widest street idea is central. It relates directly to the margin. We need to define maybe 3 critical terms here.
Okay.
First, the hyperplane. That's the decision boundary itself. It's the middle of the street. In 2 dimensions, like our dot example, the hyperplane is just a line. In 3D, it's a plane, and so on.
Got it. The divider.
Second, the support vectors. These are the data points from either class that are closest to the hyperplane. They're the dots right on the edge of the pavement, effectively defining the edges of the street.
The ones propping up the margin.
Precisely. Which brings us to the third term. The margin. That's the perpendicular distance from the hyperplane out to the closest support vector on either side. It's the width of the pavement on each side of the central line. And the entire optimization goal of SVM, at least in the simple case, is to find the one hyperplane that makes that margin as wide as possible, while still ensuring that all the red dots are on one side and all the blue dots are on the other. Maximize the street width.
That sounds perfect. If the red dots and blue dots are cleanly separable by a straight line, by a simple hyperplane.
Oh, yes.
But as we know, real-world data is almost never that neat. Points overlap, things get messy. How does SVM cope with that?
Right. That's where SVM gets really clever. It has 2 main solutions for this non-linearly separable situation. First is the soft margin.
Soft margin.
Since perfect separation is often impossible or maybe even undesirable because it might lead to overfitting,
Right.
the soft margin allows the model to, well, tolerate a few misclassifications. It accepts a little bit of imperfection. It lets a few red dots perhaps stray across the street into the blue zone or vice versa.
So it compromises purity for a potentially wider, more robust street overall.
Exactly. It's balancing the trade-off. Maximize the margin width versus minimize the number of misclassified points. It aims for better generalization. The second solution is maybe even more ingenious. The kernel trick.
Okay, the kernel trick.
What's that? Well, if a straight line, a linear hyperplane, won't work in your original feature space, say 2D, the kernel trick conceptually applies complex mathematical transformations. Think of it like putting on special glasses or using a mathematical lens.
Okay.
These transformations project your data into a new, often much higher dimensional space. And the magic is, in this new higher dimensional space, the data points that looked all mixed up and inseparable in 2D might suddenly become linearly separable.
Whoa.
So the SVM finds a simple linear hyperplane in that higher dimensional space. But when you project that boundary back down into your original 2D space, it looks like a complex, nonlinear curve that perfectly separates your messy data.
That is genuinely clever. So it finds a simple solution in a complex space, which translates to a complex solution in this simple space.
You've got it. It allows SVM to handle incredibly complex boundaries without explicitly calculating them in the original dimensions.
Wow. Okay, we've really covered a spectrum here today. From linear regression using OLS to just minimize errors, to logistic regression using MLE to maximize the likelihood of what we saw, then into non-parametric approaches looking at distance with KNN and optimizing purity with CART decision trees. And finally, SVM's maximizing margins, either by allowing some errors with the soft margin or by using the kernel trick to find nonlinear boundaries.
And if you take a step back, underlying all these different strategies, all these choices, is the fact that, as the source materials kept reminding us, prediction error is always there.
It's unavoidable.
In every single one of these algorithms, we're fundamentally managing that error, whether we're squaring it, maximizing probability around it, measuring distance to neighbors, seeking purity, or even explicitly tolerating it, like with the soft margin. It's always about dealing with that inherent imperfection.
Which brings us neatly to our final thought for you, the listener. If we accept that perfect prediction is impossible, that every model has flaws, we saw the soft margin approach in SVM deliberately chooses to be wrong for a few specific data points. It accepts errors.
For the greater good, so to speak.
Right, in exchange for a potentially better overall generalization, a wider margin. So here's the question. Does the most useful, the most practical machine learning model sometimes need to strategically tolerate being wrong, accept some level of error in the short term, to achieve the greatest robustness and utility in the long run?
It's a deep question about the nature of modeling itself.
Something to think about as you dive back into your own data and models. That's been our deep dive into the core tools of supervised learning.
Thanks for tuning in.
We'll catch you next time.